So it may look kind of calm right now, but if you had been here a week ago, there was about 60 people here at what we call Stove Camp. It's a week where we take every year and we just investigate some serious subject. And this year we are investigating mostly charcoal stoves, mostly for Haiti and for Africa, but for anywhere in the world. But right now we have design principles for our rocket stove, which is mainly a wood-burning stove, but there really aren't design principles for how do you make a very efficient charcoal stove. So we spent the week coming up with what is a design principle for charcoal stoves. So we spent the week testing and looking at different designs and really had an amazing week of really looking at what makes a charcoal stove efficient and what can you do, and if someone out there in the world now wants to design a charcoal stove, they can look at these basic guidelines of what makes a charcoal stove efficient.
This stove not only saves 75% or 80% of fuel, it pollutes over 90% less than an open fire. It burns so hot, it's over 2,000 degrees Fahrenheit in the combustion chamber.
Wow.
And it's burning up everything. So there's almost no particulate matter, there's no carbon monoxide, there's no carbon dioxide coming out of this unit. When it's burning, there's no visible smoke. And because of the way it's constructed, the stove body remains cool to the touch while it's cooking, so we don't get, there's a lot of little kids in the developing world with horrible burns from stumbling around open fires.
This is Peak Moment. We are living at a peak of human innovation, information, wealth, and health. But we're also at a peak of population and consumption, with rising temperatures and declining resources fueled by cheap oil and gas. Peak Moment Television, bringing you examples of positive responses to energy decline and climate change through local community action.
Hi, welcome to Peak Moment. I'm Janaia Donaldson. I've heard about rocket stoves or good efficient wood-burning stoves for developing countries, but I'm starting to think we may find more of them in our country. My guest today is Mike Hatfield, who's with the Aproveccio Research Center in Cottage Grove, Oregon. Thanks for joining me.
You bet, my pleasure.
And give me all the titles, your titles. What do you do?
I'm a stove consultant, which means I go internationally and help people build fuel-efficient wood stoves in the developing world. I'm also an instructor of appropriate technologies in general, so about 10 different subjects of what's called appropriate technologies at the Research Center, Educational Center.
Let's back up for a second. What's Aproveccio, and what does it mean?
So Aproveccio is a Spanish word. It means make good use of, aprovechar, from the verb. And Aproveccio is an educational center and a lab now doing research, particularly on stoves. And it was born about 30 years ago with the development of an improved cook stove, and then from that time to now has really focused largely on the cook stoves, but then has now branched into a wider range of sustainability issues, from permaculture to organic agriculture, sustainable forestry, and like I said, a wide range of appropriate technology subjects.
So appropriate technology, just give us a little, what is that?
Yeah, so appropriate technology is a term coined from really the Gandhian revolution in India, where the people of India were able to take back local control of their means of production of both clothing and salt. Those are two big examples that were illegal. And by just taking back those means of production of getting their needs met, they were able to gain independence and become their own country. So that term now is applied to technology of the sort where you have local control. No one can remove it from you. So we have alternative technologies such as solar panels, which are really great, but if a solar panel breaks or the inverter breaks, you have to pay whatever somebody wants to. So a low technology is something like cob building or low-tech stove.
Cob is what?
Sorry, earthen building.
Okay,
so earthen building
buildings,
techniques where you can dig the soil out of your backyard or in the sand from the river, and you can all of a sudden produce a house. So in other words, appropriate technology is something that's in your own control and no one really can take it away from you.
We are going to need a lot of that as we localize.
Definitely.
I mean, it's going to have to take it because the big industrial model isn't going to last.
No, exactly.
forever.
And it won't last forever. And when it falters, the suffering that comes from that can be immense. So the idea for our food systems, for our energy needs, for all those needs to have local control is, besides the fact that it's wonderful and fun and empowering, it is also going to benefit us in many ways as far as the suffering.
So you said Aproveccio got involved early on in in the stoves.
Yes.
Right. And so take us, what is a stove?
Okay, so let me give you the quick thing is that basically in the late 70s, there was an earthquake in Guatemala and about 6 people invented a stove named the Lorena stove. And it was really beautiful, one for local materials, but at that point it was just a bunch of artisans and there wasn't science involved. So basically they built a beautiful stove, but it turned out it wasn't quite as efficient as they thought it was. But they made a lot of money doing the consultancy work before that got found out, and with that money they were able to buy a research center. So luckily, when they found out the stove needed improvement, they were able to have the land and devote themselves to research. And that spent the last 25 years really of really finding out how to make an efficient stove that I'll get to in a second. And then now has returned to doing international work as well as a wide range of other things that I just talked about.
So that's Approvecho. Started from that
stove work and then
Okay.
purchased the land and became a research center in a wide range of topics.
Okay,
And
okay.
then now is
Doing a lot.
use that research center really to use science to really develop what a stove should be, and is now in the world building stoves as they should be once we've had the science married with the experience in the real
on the
world.
ground.
Yeah, on the ground.
Okay.
Yeah.
Okay, let's take a second and show me the anatomy and how it works, how a rocket stove works.
Okay, great.
Okay?
Yeah.
You want to do that?
Yeah. So Approvecho originally created the stove that was local materials called the Lorena stove, but it really didn't look at design principles of what makes a stove efficient. So what Approvecho spent really the whole 80s and then into the 90s really looking at, as well as all those other subjects, was what is efficiency in a stove.
Okay.
And what it comes out is there's really two aspects of a stove that makes for the efficient use of fuel. And that's really the combustion chamber. So if you take wood and is potential heat. This is nature's battery, right? 40 years or so, this has been storing solar energy. So you have a lot of potential energy. So combustion turns that into heat. Well, then the heat needs to be put into what you're trying to heat. So those two sides are combustion efficiency and heat transfer efficiency.
Okay.
So
efficiency in using your material well.
you want to have this be into the pot, into what you're trying to heat. So how do you get that into heat? Is two ways. There's turning this into pure heat, that's your combustion efficiency, and then getting it into that pot, that's heat transfer efficiency.
Okay.
As it turns out, combustion's relatively easy to do to get 90+%. It's the heat transfer for fuel efficiency that's a real difficult point. So at Approvecho, we do work on both sides, but I'll explain why at the second side. But for fuel use, the magic really is getting the heat into what you're trying to heat. So in the example of this stove, there's a griddle. This is a tortilla stove for Central America. We have a perfect sized gap underneath here where the heat is forced really close to the griddle. And below that griddle is insulation, which stops the heat from passing into the stove body.
Okay, let me picture this.
Yep.
There's this metal surface.
Metal surface.
We're going to cook on this.
Yep. And below there is
And
this
there's
very
just
small
a
little gap
of air.
where the
Just
air,
enough-
the hot gases pass below.
Okay.
And they have to go into that griddle because even
'cause
below
it's coming up.
below that is insulation. So we have wood ash or vermiculite or many different materials that don't let heat pass through, forcing the heat only to go into the griddle. And so you have higher temperatures and a really small little close places causing those gases to pass really close to that griddle. So that's called heat transfer efficiency, and that's really for fuel efficiency where we get our high efficiency numbers. But I do want to point out that the combustion chamber itself is also a very important piece of the puzzle for health. So our
health?
Yes, our funding actually comes more from health concerns than it does for a fuel use. And the reason is because the World Health Organization did some studies and found out the leading cause of death for kids under the age of 5 on this planet is respiratory illness.
From smoke?
Well, from many different things, but the
Okay.
chances of getting respiratory illness are up to 8 times greater if you're in a household with a traditional wood-burning fire. So think about the kids during the developmental time of their lungs are hanging out with their moms. Either in the backs or even around their legs. So during the most developmental times, they're around smoky fires. So basically that kind of says that the chances of getting respiratory illness are pretty directly caused by smoky indoor fires. So when that was kind of everybody knew that smoke was bad, but when those numbers were really put down there, and it was discovered that was really the leading cause of death for kids under the age of 5 on this planet, funding came in and people really got behind stoves, less so for the fuel efficiency use, but for clean combustion.
Okay.
So we do that in 2 ways. We have a chimney, that's ideal, but many of our people that need stoves, or the 2.6 billion people that need stoves out there, can't afford a chimneyed stove. So we really want to look for how can you clean up a stove that only costs $10. If you want to look for a market stove, it has to cost less than $10. So in doing that, we do with our rocket combustion chamber. So what is a rocket stove is what makes a rocket stove is a combination of principles. On the combustion side, it is this rocket combustion chamber, which is really a small combustion chamber that lends itself to people who use small pieces of wood. So instead of like in a big log that doesn't like to burn, you tend to use smaller sticks because you have a smaller combustion chamber.
Okay, and it's open here, and you
It's
just
open,
keep feeding it
keep
in.
feeding in, and that way the fire only really burns at the tips. So instead of this large log, and wood only really burns at its surface. So a
Right.
big log has that cool inner log. I mean, you
Yes.
don't think of it as cool, but for a fire which wants to be 600 degrees Celsius, that's cooling it down. So small pieces of wood tend to be put in because you have a small combustion chamber,
Okay.
sized for the cooking task. We also usually have a shelf, and this is if this would sit on a shelf, all our designs have shelves. Air gets brought underneath, preheated air, and regulated the amount, so it's a very simple carburetor. And then the final thing is that this combustion chamber is insulated. It has insulation around it. So this has either wood ash or vermiculite or pumice, something not sucking heat away around it. So between this wall and this combustion chamber is a 2 to 3 inches of insulation.
Okay.
So the temperature, so all those things that cool your fire, which is the stove body, the large pieces of wood, and excess air, are reduced in this very simple design called the rocket combustion chamber.
Efficiency.
Yeah, efficiency for combustion, and then once you turn that into heat as much as you can, so you have very little smoke, you efficiently put it into what you're trying to heat. So if it was a pot, it'd be a skirt, which forces the flue gases around.
Okay.
If it was a griddle stove, it would be just this small little space below. And so heat transfer, combustion efficiency, in design principles, that's a rocket stove.
Great. Thank you.
You bet.
Now, I noticed you had examples of portable
Yes.
rocket stoves. Can
Yeah.
you show that to us?
Yeah, let's go take a look at some of our stoves.
Let's go.
So here's one of our examples of our stove designs that we work with in the world. I was talking about, I showed you one example of the Husa stove earlier, but this is what we call an institutional stove. So many places like orphanages, schools, they cook very large amounts of food. So we design stoves that cook up to 200 liters. Wow. But this is an example of a 60-liter stove. So here's the size of a pot that would be 60 liters. So
So here's this is the
stove.
stove, and here's your little combustion chamber.
Yep, and let me pull
right?
this. Yep, and so here would be a pot example.
Oh, wow.
Yep, so that's 60 liters.
Phew.
Those of us some people are liter challenged.
Thank you. Yeah.
It's a 60-liter pot, and like I said, some institutional stoves get built up to even 200. But this would be a nice size for a nice sized school or orphanage or market. Somebody's cooking food, and so as I talked about the design before, and like all our rocket stoves follow in those same principles of good combustion and then good heat transfer.
Okay, so this is where the wood gets
goes in.
fed
So
and
remember
on the shelf.
Yep. So earlier I talked about the
Oh.
fact that it's sized for whatever size cooking task. So this one's slightly bigger than the other combustion
Right,
chamber because it's
right.
a slightly bigger task. But we still size it to whatever the task is. And then we have the shelf, so air has to
I
pass
see
below.
that. There's a little air gap.
So really, we call that a simple carburetor in the sense that the fuel to air mixture
Okay.
is regulated. So you fill this full of high power, full of wood, and the amount of air coming in is the correct amount of air, and the air gets preheated, and you have this little riser inside where the combustion happens, and it's insulated, as I spoke before.
This whole thing is
The
insulated.
whole thing is insulated. So we're going to take a look at the inside of the stove a little more detail here.
Oh, okay.
Right, just because then we can look
Oh.
at. Yep. So looking down, you see this is a high temperature stainless steel combustion chamber.
Now, is this
It's
is
full
this
of
empty?
insulation. Nope, it's
full
filled with insulation. Yep.
So the wood is down in here. At
Yeah,
the
the
bottom.
wood enters in the bottom,
Okay.
and then it burns at the tips, just like in the other stove.
Right.
And in this area, it gets complete from combustion.
Okay.
So while it's rising up, before it hits the pot, you get that complete combustion. Then once you have that complete combustion, then you have really good heat transfer.
And so this
right.
is metal too.
Yep. So by the time it's hit the bottom of the pot and come out, it's dropped in temperature enough to where we can use a milder metal. So high temperature stainless, or we can use ceramic. And then once it hits the pot and gets cooled off a little bit by giving its heat, you can use a milder steel.
I see.
So then, but the really important thing, similar to the griddle I explained earlier, is that there's a perfect little gap to force those flue gases close to what you're trying to heat. In the griddle stove, it was that metal griddle.
Right.
In here, it's going to be that 60-liter pot. So the 60-liter pot sits inside, and it's hard to tell, but there's a little tiny gap.
Yeah, I was going to say, I see that down here you've got a little.
Well, that's a secondary gap. So let's look at the first gap. So if the pot sits in, you would actually notice that there would be a small gap. We're talking about 1 centimeter.
Oh, really?
Between this wall and where the pot's going to sit.
Okay,
And that's
okay.
where the flue gases actually come up, and they originally give their heat to the pot.
Okay,
Right. So
okay.
lots of surface area. Then we have this is a chimney stove, so we have a chimney exit down here. So the gases are going to be pulled from. I'm sorry if you can see the stove with the chimney. So
the big stove.
So the
I
big stove
see.
has a chimney. It's going to actually come down from here. So the gases are pulling out of here. So there's this outside gap where the gases now have to round the corner and get pulled all the way down the stove.
So they get sucked down the
Yep.
stove, right?
Yep.
So they come up,
Yep.
make sure I understand this.
Yes.
They transfer into the pot
Pot.
in this little area,
Yep.
up and over this little lip.
Yep, and then they come
down
down
here.
and then collect and go out the chimney.
Okay,
And s-
okay,
But
okay.
but this does something amazing that sometimes people get or don't get, is that heat that's going up here wants to go anywhere that's colder. So it goes in the pot because that's colder, but now it can't go out because those gases that are going down are pretty much the same temperature.
Okay.
So in other words, that heat is now, it's going mostly into the pot. So it's really high heat transfer efficiencies, we call that. And then outside that downward gases, we have insulation. So we have more insulation.
So you're not going to get burned.
You don't
or
get,
whatever.
you don't
It's
get,
like
so you don't get burned, so that's safety. And then
Yes.
you also have the heat only really can go into the pot.
That's really
So
so
super
you just
high
keep
heat transfer efficiencies.
directing it
Yep.
both from
Yep.
underneath and from the sides.
Yeah, so we have some examples of stoves, institutional size stoves. One example I always show a photo of in my slideshows in Malawi, where there was a school that used 95% less wood to cook. So this amazing photo of what they cooked for these, I think it was 60 or 80 kids, and every day they used this much wood now, and before they used 20 times that amount. So this big pile they show daily they used to use, and now they use. And so when you start multiplying that in the hundreds, that's an amazing amount of wood
Sure.
every day. So
And in wood scarce areas, that's going to be critical.
critical for sure.
Really.
So, so this is a really one of our really highest efficiency designs, and I want to introduce you to Fred, who is really running this project.
Oh, fabulous. Okay.
Yep. So this is Fred Colgan, who is starting Colgan Stove Works, which is this project, and yeah, I'd love to have him explain really what's going on here.
Great.
This stove came into being because my partner, Damon Ogle, went to Uganda to try to build this stove in the developing world, in the field. And he realized it was very, very difficult to build to the precision necessary for this stove, which is 1 millimeter of tolerance. It's very difficult to do in the developing world without some specialty tools. So Damon came back, and we've been building this system for constructing these stoves for the last 3 years. We start with laser cut parts, which is really the high-tech part of the stove. This is a laser cut piece of 310 stainless. This is what the combustion chamber is made of. It's very expensive metal, but it's the only metal that'll withstand the temperatures we generate in the combustion chambers. Then everything else in this shop is very, very low-tech and easily transferable. Our goal is to get precision stoves manufactured using local labor in the developing world.
So do you give them the parts? I mean, you cut out the parts and they assemble it?
Exactly. We've created, if I could show you over here.
Sure. I'll follow you.
We've created a series of tools and jigs like this which make precision construction possible. So this is the basic layout jig. The barrel gets inverted on this, and
Let me back up.
Okay.
The barrel is a standard.
Well, yeah.
Sort of?
These are recycled steel drums. I
Wow.
found from some guy down in Utah.
Okay.
And they're perfect.
So you-
invert the barrel on the jig, and all the layout happens here. So the combustion chamber is in exactly the right spot. All of the various pieces of the stove are laid out within this 1 millimeter tolerance range, so that we have a stove that will perform like it's supposed to. And it's interesting, in stove building, 1 millimeter is a very small distance, but a 1 millimeter mistake in constructing this stove could mean a 20% loss in fuel efficiency. We're talking about very, very tight constraints. So to make a good stove, we developed a system of transferable technology.
So now, does this this place where you put all the parts together, right? Is this then brought to the third world, the other developing country? And,
Exactly.
And
yeah.
then do they attempt to find some of those materials there, or do we?
It would really depend on the local situation. We're working on a project now in Nigeria, so the first step is I will go there and see if I can find a local barrel source, see what materials I can find on the ground there, and then we will build the tools for that project, ship whatever parts they need. Clearly the laser cut parts, they're not available.
Sure.
And then go and train the people who are going to do the production and continue to ship the parts so that we can make these stoves and create a viable business in the developing world and a stove factory that should be able to produce these in any number that the market will bear.
Behind you, you know, we had it here before. You've got this shelf full of, what are these? The combustion
These are
chamber?
combustion chambers.
And so my question is, do you ship this whole already built combustion?
No, we'll ship them flat. We'll ship
Just
these parts flat.
pieces.
And we have jigs for assembling these. It's a
Okay.
very simple tooling. The only electric tool for this is a spot welder, which
Yeah, I
is
see the little weld spots
Yeah.
here. So they can just get the flat pieces from you, and the jig will assemble this around and where you weld.
yeah, it's all handwork.
Oh.
It's all handwork, but it's not skilled labor. It's more like semi-skilled.
Yes,
And
yes.
reasonably talented people can learn how to build these stoves in a week or 10 days. I had a workshop here last week where 8 people came into the shop who had never built one of my stoves before, and they built 2 stoves in 4 hours.
So part of your work then involves the pieces, the jigs to set up stove factories in other countries for
Exactly.
people to do, to help their own countries and to have businesses that are viable and everybody's winning is what
Exactly.
I see.
And to get these stoves out there, this stove not only saves 75% or 80% of fuel, it pollutes over 90% less than an open fire. It burns so hot, it's over 2,000 degrees Fahrenheit in the combustion chamber.
Wow.
And it's burning up everything. So there's almost no particulate matter, there's no carbon monoxide, there's no carbon dioxide coming out of this unit. When it's burning, there's no visible smoke. And because of the way it's constructed, the stove body remains cool to the touch while it's cooking, so we don't get, there's a lot of little kids in the developing world with horrible burns from stumbling around open fires. And the chimney gets the smoke, whatever little smoke there is, up out of the cook's face and out of everybody's faces. So,
Wonderful. Thank you.
You're welcome.
This is really inspiring, both your manufacturing model and, of course, the stoves themselves.
Thank you.
Thanks. I want to go back and have and see some more of the testing that
Yes.
happens in your group.
Yes.
Thank you.
Good.
So besides Aprovechos implementing and designing stoves, another big part of our work is basically testing stoves or having people send their stoves to us to test and teaching them how to test stoves. So basically, here's a selection of some of the stoves that we've had sent over here. We've had hundreds of stoves sent to the lab to be tested over the years. And we test them here for emissions and fuel use, and then can make them some design recommendations of things they can do. And then besides that, we also are creating testing centers like Aprovecho around the world. So let me take you over to some of our equipment here, and I can show you the equipment that we use here to test, and also what we are sending out to create what we call regional testing centers.
So what you're doing is you're empowering local people to do their own testing?
Yeah, exactly. So in every area of the world, people, instead of having to send their stoves to Aprovecho, could send it to a regional testing center or go to that regional testing center to be trained on what makes a stove efficient, what makes it clean burning.
great.
Yeah, it's great. So we have a relatively inexpensive set of equipment that we produce here at the at the lab, and it actually folds up into a suitcase size box to be shipped or be brought with somebody in their travels. And it really consists of nothing more than a cloth, a simple cloth, fireproof cloth, where we collect the smoke through
Right, so you put the stove goes down here.
Stove is
right, and
yeah.
you're burning it.
Yep.
Or
You're doing
rules?
we have a water boiling test. We have a protocol of testing called the water
okay,
boiling test.
okay.
And in that test, you basically the smoke gets drawn off. It gets drawn off through a couple simple apparatus that we've created that basically measure for particulate matter, which is very dangerous for, like I said, the lung disease of kids, and then carbon monoxide, which is also a very dangerous poisonous gas that comes off stoves. Those are the two main issues that wood burning stoves have: particulate matter, carbon monoxide, and then we also do measure
Carbon
CO2,
dioxide, right.
CO2,
Right.
and that's mostly for global warming potential and fuel use in general.
Okay.
Yeah.
And that just folds, and that whole thing folds
Folds up, and actually all this really is made to nest and fold up into a regular suitcase.
cool. That's
Yep.
cool.
So in one suitcase you get all this testing equipment, and
So do they have to have a computer to do it?
They do have to have they have a computer, and we created software and an Excel spreadsheet that
okay.
people have to plug the data into. So, but every regional, anybody of that level of skill and at this point that we work with does have access to simple computers, does have access to some skill sets such as Excel use. So that is a minimum requirement to be a stove testing center, but it's not that high.
You must feel really satisfied.
Yeah, it's a
at
pretty amazing
the
work.
changes that this center, this little humble place, really, are doing all over the world.
Yeah, it's pretty magnificent. Sometimes it's easy for me to forget about it, but then every once in a while I'll step back and think about it, what we're doing in the world, the role we have, and it's pretty exciting.
You're saving lives, and you are paving a way for the future with appropriate technology, empowering people where they are.
Yeah.
Good work. Keep it going.
Thanks.
Thanks for being with
You
us.
bet. Yeah, it was a good day. Thank you.
You're watching Peak Moment, locally reliant living for these challenging times, and I'm with Mike Hatfield at the Aprovecho Research Center in Cottage Grove, Oregon, with really amazing wood stoves. Take care.